Okay, so today's topic is about timers, and not just only timers, also, let's see, also interrupts and PWM. Okay, so lots of good stuff. Fundamentally, the second exercise continues the first exercise. So first, you need to finish the first exercise, and then after that, clone that project and continue to the second exercise. But anyhow, I will show you, even if you haven't finished the first exercise yet, don't worry, you have still until Saturday to do it. Well, make notes. Oh, should I actually turn the projector on? That might actually help a little bit of the maybe a bit. So today we have lots of good stuff. So basically, yesterday the program was timed by the sleep timer. Okay, so today we actually use some other timer, basically making a normal timer there to give interrupts at rate about 2 Hertz. Okay, and use that actually so that the interrupt service routine would turn on and off the LED. So in principle, today's topic is to make this main loop, the while loop, empty. So nothing happens on that while loop. And all the functions are happening via interrupt service routines. Okay, so basically the timer interrupt runs the LED. Then the pin information actually would be added there to give the interrupt on rising edge of the button press, and then again nothing happens on the while loop, but we need to find another way of passing the information that this button is pressed. Okay, and basically LED blinks only 10 times after the button press. Then the fourth task is about PWM and turning a servo. Fundamentally, the servo is very simple device. There have been this kind of standard servos what we have, like this small servo 9G model 9G, which has very limited the torque. But well, this is good since we don't need external power to run it, so it doesn't take much of power either. Right, so basically the servo is very simple. Let's see, simple device. All right, let's see the present here. Servo motor control. Okay, device which transfer an electric signal to mechanical position, used in toys, robotics, wherever you need an actuator at low cost. The standard signal is very simple. You just have the power and ground signal, and then this basically pulse width modulation what is used there. So, or actually duration of the on state defines the angle. And that's okay. So the so-called standard servo does not exist. All of those are a little bit different, but usually the mid angle is at when you have the pulse width is 1.5 milliseconds, and minimum is usually, well, in cheap toys it's you get the minimum angle at 1.25 milliseconds and maximum angle at 1.75 milliseconds. But actually this can actually range from 1 to 2. That's quite common also. The problem of running it on too short or too wide pulse is this actually can get mechanically stuck if you run it on full tilt on either of those edges. Cheap servos does it. And guess what we have here? This is the state of the art cheap servo. Okay. Yeah, so very simple device. You just have those 3 wires and pulse width. Pulse width is telling the angle, for example, from minus 90 degrees to plus 90 degrees. Okay. And the full period must be, say greater than 20 milliseconds, but it cannot be, 1 second. Then it usually the servo doesn't do anything. But around 20 milliseconds, that's fine. All right. So, but let's tackle first the problem with the interrupts. How the interrupt mechanism on PSoC actually work. And what? Freeze. Mute. There. Good. So, this is 8-bit RISC processor, which has a, on the beginning of the memory, there's a boot table or interrupt vector table. So this is the first address right here, 0000 0x hexadecimal, and then basically each interrupt reserves 4 bytes. The first interrupt is the boot interrupt. So how a microcontroller boots on reset interrupt. So it jumps on the first address here and starts executing. So if you don't use any other interrupts, you could actually put all the code here. But if you have actually, if you are using the next interrupt, with this second highest interrupt, I think it was the I think this interrupt actually has to do with the power. Yeah, on this processor. Yeah, on this processor, that it has this low voltage detector to protect the from brown out of the circuit. So that interrupt is here. So that's the reset interrupt, and that's the low voltage detection interrupt. And then I don't remember exactly, but there's basically all of these interrupts will take 4 bytes, and during that 4 bytes you must have a code that jumps into certain address. And here actually is a command long jump to boot. Yeah, yes, long jump to boot. Remember yesterday I showed a file called boot.asm. Okay. Actually, I think this reset table is on the beginning of it. But anyways, on boot, there's that code where the reset will actually go. Okay, so similarly, we have one of these vectors here is pointing into the code, for example, for the GPIO interrupt. So the IO interrupts fundamentally. And practically only one interrupt for all of the pins, which means that when we have a interrupting pin, then any of those will cause the GPIO interrupt, which means basically here we have a long jump to, I think it's PSoC GPIOINT something, which is also another piece of code. That's, well, I need to open it, but anyways, there's a corresponding ASM file ending at int. So any of those actually work like this. So if we have an XX interrupt here, then basically there is on these 4 bytes, there's long jump to XX int service, which is an assembly file. Okay. And this is automatically generated. At somewhere in here, there's a commented section saying that put your code below and put your code above. Okay, since nobody actually wants to make any the interrupt code on assembly level, nobody, believe me, not even me. So basically, this is all is automatically generated by the tool, and when we have this interrupt happening, this actually jumps into that routine and does all kind of nice bookkeeping operations. But here you must have a jump, or either long jump or call of your own routine, which is in say, okay, either long jump or long call to underscore my ISR in C. Okay, whatever your code is in C language. So basically, that now you have your own code somewhere where you have a void function of my ISR in C, where you basically do whatever is needed. The difference between long jump and long call is that if it's a long call, then it basically it means that this routine here is a normal function, nothing fancy about it. However, you can also do a little bit faster code, not much, little bit, but not returning here at all. But in here, you do a return from interrupt instead of return. Okay, I should probably use another color here. So if you are using long jump, then you must have a pragma statement, which is again compiler directive for extra stuff. Pragma interrupt handler and then the name of that function. It doesn't fit in here anymore. So you basically, at the same way that on this GPIOINT.h file, there's that definition of those IO ports as pragma statements. Pragma IO port, that mnemonic, and which address. The same way here we can say pragma interrupt handler and the name of that function. Then instead of return, that this actually returns from interrupt. So at the end, well, I'll just put it so it uses return from interrupt instead of return. If you mix those, so make a long call to this kind of function, you will get Stack Overflow in a just few hundred, just in tens of instructions. Just about 20 the interrupts and you are done. Yep. Well, then how about standing up? Good exercise. Okay, so this is the interrupt mechanism. Okay. Then basically on the interrupt mechanism, there's also the control of which can be giving the interrupt. So each of these interrupts actually, well, the reset interrupt is always on. so is the low voltage and watchdog and that kind of interrupts. But any other lower priority interrupt actually have a the enable GPIOINT. Or something like that. There are actually routines that enable exactly that interrupt. Okay. And in addition to that, you of course you must have the HC enable global interrupts. How did it go? I have terrible memory. but anyways, this is easy to remember since that's generated always on the as the first line on what you will uncomment on your code. So these two, and then this interrupt is working. Okay. Yep. So no magic on interrupts. There are still a couple of small things on the interrupt actually. The let's see. Especially the button press may generate a lot of interrupts unless you do debouncing of that interrupt. On this application, I think the debounce is not necessarily required, but usually it's quite good idea to do the debouncing logic there. But I can give you some hints on, for example, on whiteboard. Oh. Okay. So debouncing. So the problem on mechanical switch is usually that, let me put the same picture I had yesterday. So this is a mechanical button switch, and this is a PSoC, which has the inside you have the pull down resistor. When you switch that one on, actually what will happen as a function of time, you think that you're actually touching it like that, but there's no spring or nothing. So basically it does start bouncing like that. And finally it's stuck there. The same thing when you release it. It doesn't release immediately, but there are, say, this kind of things happening usually also on that, on the other edge. So you can get rid of these by when you have this interrupt happening, for example, on rising edge interrupt. Then basically the first thing what you do, you would disable that particular interrupt for a certain amount of time. That would help debouncing of that one. But of course, okay, there you have another on the other edge. So for this kind of application, I would make the disabling of the interrupt way so extremely long. Let's put it this way, as long as needed. So in the application of this exercise, that the light must blink 10 times. So basically, you would, on this interrupt service routine, you disable that interrupt. And then when your blinking is done, you enable it again. And here. That'll work. After the function is done. Another, actually, if on a generic place or a generic application, I would do a timer for another timer for making basically the debouncing. Good. That's quite simple, actually. Let's see if we can remember it after when you're doing the exercise. All right. So next, I will go through a couple of things on the PSoC designer. Okay. So on the PSoC designer, there. On the PSoC designer, actually, our yesterday's project is right there, recent projects. Clicking it once does open it, I see. Okay, but we are not continuing on that on this mode, but we go and actually do a new project by cloning existing project. So yesterday we started from scratch a new project. Today we will clone the yesterday's project, which was there, PSoC EX1 anti-KP. That file, CMX file. Name, all right, what was the yesterday? PSoC exercise 2. Like that. And now we have a safe copy. Where to continue? Okay, and this actually has all the needed, the LCDs and LEDs. Sleep timer we don't need today, unless you want to actually have, instead of sleeping on that, well, instead of just going fast on the main loop, you can also actually do some sleeping on the main loop. It doesn't make much difference. There is actually a small, since the sleep doesn't consume any computing power, so the power consumption goes down when the processor is asleep. So basically, we could still use the sleep timer. Let me go to and see the not boot.asm, but well, the that one. Okay. So, hey, I have my while loop is ready. Since for the second exercise, we don't need this one. So this is empty, or just sleeping here. So sleep to conserve energy. Okay, so fundamentally on this main program, I just need to make the starting of the modules and set up the interrupts. Well, yesterday you already tested that you, or the first exercise said that you already tested those devices, so you know that they should function. Okay, so we need to actually add only this timer here first. Let's see, timers. And now we need to do some calculus. In order to get about 2 Hz interrupt rate. And we have actually 2 clock sources there. 32K clock, internal 32K clock on the global resources. So that could be used. So basically the divider to get 2 Hz would be, it's 16K, which is 2 to the power of 8 is 256. It's 15. I'm not too good on the 15. Is it 15? 14. Yeah. Okay. Yes. You're right. So it's about power 14. So that's the divider for our clock divider. We start from this one and divide it by the to the power of 14, which means a 16-bit counter. And this one would be giving the interrupts. Ha. Good. So we need 16-bit timer. Just add it there. And actually change the name. Okay, change the name to say 2 hertz. Has 2 hertz timer or something, descriptive. R2D2. All right, and there we actually start selecting kind of things. Do we have a, yes, CPU 32 kilohertz. Clock source 32 kilohertz clock. And capture. Okay, there's a capture mechanism about the how to restart the timer. Let's check the data sheet, what it says about that parameter. At least I need some reassurance that parameter works as I think it does. Placement parameters, capture. Okay, the software capture mechanism will not operate correctly if this parameter is set to a value of 1 or is held high externally. I would say we use low state for that. And we basically are not interested about the current count register value. We are just using this as a running counter and do nothing until this one interrupts. Okay, so capture low. Was it like that? Say will not operate correctly if this parameter is set to value of 1 or held high and external. Yes. So if it's held low, then it should be fine. Okay. Terminal count. Basically, we can take also the terminal count signal out of this device, but we don't need that signal. We just use the interrupt. Compare out. Well, okay, the same module can be used as a PWM. So the compare value is basically just giving this high state when we have this count is less than this terminal value. So we just basically compare out also. Done. We are not interested about that one. Period. Okay, this is what we need. So 2 to the power of 14, which is 16,000 and hey, you should know this by heart. Yep. -1. Because first count is 0. 0 to that value. Or actually, there's also the, I think it must be like that. On the other hand, 2 hertz, this one, it's change. It's not that much. In a real-time clock, yes, but not in this. Compare value doesn't matter now since we are not using the compare to get the PWM pause. Compare type, either or, less than or equal is just fine. Interrupt type would be terminal count. Terminal count. When when it hits the end. Clock sync usually you can actually check it from datasheet, but most of these cases you would use sync to system clock. On some rare occasions, actually, you can sync it to something else, but that usually means that you have external clock running this. But if it's internal clock, then you want to synchronize it with the system clock. And TC pulse width really does not really matter here. Terminal count pulse width doesn't matter. Invert capture. Okay, so meaning PWM, which side is it? This way or inverted? Good. So in principle, now we have the timer set up. We just need some code. Let me generate the header file to see what kind of code we actually get there. Should we actually? Well, let's start from the boot. I'm not sure if this one actually has the. Okay, so basically, what I draw here, the boot table, it's on the beginning of that one. Yeah, low voltage detect is at 0.4, and then okay. So the next one is actually analog column 0 interrupt vectors. Okay, yeah, but anyways, each of those has some boot code, and basically low voltage detection boot means halt. Don't mess it up, since if you can actually mess it. You just put something else there. Long jump to a routine that does brown out to your circuit practically. So this halt here actually means that your system does not die. And yeah, so at memory address 0, there's the reset interrupt vector. Long jump to start, which is down below. But okay, here we have 2 Hz interrupt service routine. That's the timer interrupt service routine. Similarly, there is a sleep timer interrupt service routine, and also there would be, if we would have marked any of those pins to interrupt, there will be also this GPIO interrupt vector. And all of these actually has the corresponding assembly file, like that 2 Hz interrupt.asm. So this one here. Which looks like that. So 2 Hz interrupt. Okay. So how familiar are you with the assembly code? Not too much. Well, you can read it, right? Okay. Yeah. So these here are the same as included in a C program. Exactly the same. But in assembly, those macros and such are just called .inc. So some files to include. Then export actually means the same as extern in C, meaning this mnemonic is kind of told to the linker that hello, it's here. Yeah. Don't worry about that. That's just assembly code describing what kind of memory to use here. And here we have at some point, yes, the routine itself. And here, insert your custom assembly code above this banner. Wait a minute. Yeah, here. So preserve. Oh, okay. Yeah, the custom assembly code should be here, but I don't like assembly code that much. Okay. Now I can actually just uncomment that one and uncomment also those, since that will be actually helping you to the like that one. That helps bookkeeping of the basically the most important register values, since you don't know at which point this is interrupting. It can be at the middle of calculations. So it means that you must make a copy of all the register values so that you can return back to where it was when the interrupt happened. Okay, so now we just need to change this name to something that means something. So, for example, my C, and then what was this? This was the 2 Hertz interrupt service routine. Make a note of that. I would actually copy this function call. I copied it without the first underscore, since that basically the C compiler compiles kind of semi-assembly code where all the variable mnemonics and all the C mnemonics variables function names have the underscore in the beginning. Okay, that makes it easy to actually call any C routine calls from assembly. Then on the C programming language for embedded systems, there's always a way to include any assembly code also in the code. So it's usually ASM function that does it. All right. So that's all we need to do on this code. And let me save that one. And then somewhere you would have your own interrupt service routine. It would be a good idea to actually have another file for those. Would be a good idea, but who cares about it? I just put it at the end of the main.c. Yep. Okay. So, oops. Interrupt services. All right, there. Interrupt service routines. Like, they all are type void. Then we have this my C2 Hertz interrupt service routine, and which is also type void. So no input parameters, no output parameters. Okay, that's actually one nice trick to find or keep track on these parentheses. Just put the comment at the end of it, so it shows basically the block. Otherwise, if these functions are getting long, then you never know which parenthesis is which. You get a lot of errors. Okay, so now basically this should work to give the 2 Hertz interrupt just like that. And inside of that, you can write whatever you want. All right, so so this interrupt service routine is visited at the rate 2 hertz. Okay, where on this exercise you would actually blink the LED if key was pressed or the button was pressed. Okay. And well, you can figure out the rest. There are these blinking routines for LEDs. Let me help you a little bit more, and let's go back to the this exercise. And what was my? Was it 1.4 was my button? Okay. Currently, it's a disabled interrupt, so you need to make this one rising edge interrupt. Okay, rising edge interrupt. That's the deal. And let me generate the configuration files again to get that one very important place there, which is the PSoC GPIOINT.asm. So this assembly code here is similar to the timer, similar to the timing interrupt. So basically, you would put your custom code here, and well, I will do the other mechanism here. So I will use the long jump instead of okay. So basically, now I have long jump to the routine, meaning that I must actually I must then use the pragma statement for that interrupt service routine. All right, let's go to the save that one and go to main.c. There, and that's the way you do it. Aha. Okay. Now the question is how this interrupt service routine can know that button is pressed. Oh. We need a semaphore, bathroom key. Okay, so we actually need a global variable, a flag telling when you visit when the interrupt service routine of button press comes here. Basically, this routine just sets a flag. Now I have been pressed. Do something. And that's actually the correct way of using these interrupt service routines in any case. Do as little as possible on those interrupt service routines. If there are, say, calculations which take time, usually, if you have arithmetics, any arithmetic operation will take more time than simple operations. Then you would just have here the flags telling the other parts of the program, okay, go on and do whatever has to be done. Okay, but anyways, this one uh, on this case, I would also check if this if it was this certain button which was pressed. Since you can have different button or different input GPIO interrupts. You have up to, in this processor, you have 24 pins you can use for interrupting on GPIO. So first thing would be to check which pin was interrupting. And then do accordingly whatever is needed, and then set the flag, which is just a global variable. And okay, debouncing. Disable GPIO interrupts. This is one way. Another way would be actually have another flag on this my C2 hs.isr. Put another flag there. So basically, it would mean that we would do nothing here if the flag is on. Or use the same flag, but there are different ways of doing it. But use one which works. But this actually works quite nicely, since then it also saves a little bit of computing time, since it disables interrupts, so there's no overhead due to that bouncing. There. And the corresponding changes on this another interrupt service routine is to check if it has blinked already 10 times, then reset the flag and enable GPIO interrupts. And then it just, the processor does nothing until this button is pressed again. Ha! All right, so you just need to fill the blanks. So when you get this one done, you can pat on your shoulder. You have understood the interrupt services on this platform. Hopefully, it will also help you to understand, more complex systems platforms. Oh yeah, I almost forgot. We need that global variable, of course. It could be just, 8 bits variable. The byte has been defined on this platform as unsigned 8-bit character. Byte, and that would be the button pressed and initial value to 0. You can also use this as the counter how many times the LED has blinked. Since remember, in C programming language, false is 0, true is anything else. For example, 10 or 20. Ha! Ideas. Yeah, so yeah, something like that. That should make the just filling in the gaps would make this LED to blink 10 times. Then the PWM actually would be also on the same program. Oh, I'm, putting a lot of things there. Yes, you have a question? 32 kilo divided by 16K is 2. 16K. 16-bit counter, but you count for, yeah, yeah, yes, up to that number. It gives. Yeah, yes, yes. 16K to the power 14. That's our terminal count, the full period. Good. So, okay. Ooh, big mistake here. This is exercise 2. Then, how about the PWM? Ooh, what did I ask you to do actually on the PWM? Not that one. Okay, modify design, PWN, port 1.2, interrupt on capture. Wow. Modify your code and add your own interrupt service routine for PWM, which does the following. Excellent. So this is kind of strange thing what I'm doing here. so, so how the system should work. Okay, we have this PWM which gives that signal. Then on the time longer time scale, the angle, you would use the PWM interrupt to count actually enough of times that in 200, oh not 100 interrupts, after 100 interrupts, you would actually change the value angle. So it go like this until it hits the 90 degrees, so it starts over from here. Okay, so what should happen? What was it? Oh, okay. No. It goes down. Yeah. So it should go like this, yeah, and then back. Boy. I didn't probably have too much of sleep when I was designing. Sorry about it. It's actually after this exercise, you can actually say, now I understand PWM. Yeah. And another thing, you can then think of, okay, there was a 2 seconds on 100 counts, but how about just making gradual change? So this is basic kind of linear interpolation. You just make this one shorter and also the step size smaller. That's the way you can actually do the smoother controlled movement, basically like that, following a line. Good. So, okay, how to do that? I will give you more hints, but not all the hints anymore, since you know already how to make a hook on the PWM interrupt service routine. Another thing, you need to also calculate how to get 20 millisecond period. Yes, and okay, how much you need resolution on your count the PWM module. So what is your initial clock rate and what is your main divider? Since you need that 10 degrees, resolution in here. Yeah, you need to do some paper and pen calculations here, but it's doable. I can help you a little bit there, but anyways, everything starts from the this designer again. Add here the PWM. I will add there 8-bit, but I think this is not enough. You don't get enough of resolution. But that's the reason why I'm giving the using this as an example. The clock. Okay, now which clock to use? Plenty of different sources. It could be VC3, but then you must do the division of those initial clocks accordingly. You can also use 32K clock if that is enough, if that gives you enough of the resolution for your system. Remember about this 20 milliseconds, that's roughly 20 milliseconds. It doesn't need to be exactly 20 milliseconds. The pulse width must be exactly, or as close as possible. Okay, so just for fun, I'll use this 32 kilohertz signal. Enable, okay, enable, I think that one is high now to enable it, right? But to make sure, let's see from the parameters. Okay, yep. So it's enabling the device. It's funny, it's actually the same place parameter on the timer was, you must put it low state, otherwise it doesn't work. Compare out. Okay, now we use compare out. It must be actually routed to your output pin. Okay, output pin was 1.2. That can be actually connected on this. This is 1.2. It's odd port. Port 1 is odd, and on it can be connected in that line. Did it do anything? No, okay. It's because I have used that also as input. Okay. So for example, yeah, I can always do some other things here. So let's see, 1.4. Okay, 1.6 for example. I can connect that one here. Not there. The next one. But you do the as it's told, not as I'm doing here. 1.6 there, and then I can connect that one to that row output. I think it's this one here. So you need to do these connections, but not these connections. The connections that will help you to route the signal to port 1.2, and then that PWM output would go. The compare output would go to the row 0 output 2. There. So there we have the PWM compare output goes to the that output line. In this case 6, you would use output line 2 for odd ports, and that one is connected to the pin where you want that PW signal to go. Okay. Terminal count, we don't use the terminal count. Period, okay, you calculate the period. I just put here 100. Pulse width, calculate the initial value. I would put this middle value, 1.5 milliseconds long pulse. What is a corresponding value there? Compare type. Okay, less than. Yeah, less than, since it starts from 0. To get 20 ticks, then you would have actually less than. Less than or equal still would be, it would give you 21 ticks. Yeah, maybe. I'm just, pulling this, pulling the numbers from the hat. And I'm quite sure that this wouldn't do anything for the servo. Or maybe jam it on one end. Yeah, and then the interrupt type, actually, again, I would use the terminal count interrupt, or basically also the compare true interrupt would work also. Then okay, terminal count makes the interrupt on the end, which means that you may actually not be able to do this one until the next cycle of this PWM. But there's only one delay of 1 for that command, and it's the same delay in every single one. So it still does the same. So in this case, it doesn't really matter. If you use the compare true kind of, then it basically, when it starts comparing and you get the first true, you have the interrupt, and then you will change the compare value for the next round. Okay. Clock sync, again, we have using internal clock, sync the system clock, invert, enable, normal. Oh, okay. So that's all the things that you need to do for the PWM. And again, when you generate the configuration files, you will get also the PWM8 interrupt.asm. And now you know what you do. Either long call or long jump to your own interrupt service routine. And inside of that interrupt service routine, I'll just write a dummy routine here. Void dummy routine. Okay, inside of that one, actually, you would use a loop counter because you want to wait for 100 interrupts before you do anything. You can use global variable, but you can also use static local variables. So static local is basically you can initialize it at 0, and then after that one, basically you can use it and change the value. So you can have static byte variable loop count equals 0, and then basically just have a statement where you check if the loop counter is equal to 100 or 999. It starts from 99. Oh, actually, less than 100. So that would do also. Right. Yeah. Maybe. I use that one. Okay. Yeah. And okay, plus inside of there. Okay. Yeah. So it first compares and then the increments. Plus loop count would do increment first and then, but this is basically Oh, wait a minute. Plus plus loop. Yeah, plus plus. Yes, the other way around. Yeah. Increment first and then test. Increment first and then test if it's still less than that. And basically, this one would mean that we just return from the function. Otherwise, so this is like a game. Are we there yet? No. Are we there yet? No. 100 times. Okay. So if it is less than 100, then just return, or if that is 100, then reset loop counter and do whatever is needed. Change the angle. Okay. Angle. Yeah. So that's the main framework for the whole thing. Whoa. And then you need to fill the blanks. Good. So in principle, I have given enough of hints, at least in my opinion, for you to go through this second exercise. But if you haven't finished the first exercise, finish that one first, then continue on this one. Okay, good. Oh, sorry. I used to be a baseball player. Not really. Finnish baseball. Have you seen that game? It's really weird. It's even more boring than the American baseball, if it can be true. Okay. But okay, so that's the my show today. I will be here until around 4 o'clock, and I will have the lunch break. Was it something like 12:45? Starting from 12:45. So you are free to use the lab, but I'm out for 1 hour or so. Good lunch. Okay.